Oh, thank you very much. This is certainly the largest audience on the tour. So I've been your ambassador to a number of different universities over the past 9 months or so. I started here October 9th at the University of Calgary, and we're just about at the end. I've got a couple more planned, but this is number 16. And usually at this stage, I would show a slide showing the homepage of the CSEG, and I would encourage students to sign up for their membership and tell them about all the benefits of membership. And I do hope that this tour, in terms of raising the profile of the CSEG, has done its bit. So it's certainly been personally a wonderful experience, and I've learned a great deal about what other universities are doing in geophysics. And so I thank you for that opportunity. So let me get on with the talk itself, and the proper emphasis here is what else can the seismic waveform tell us? Because we all know that the seismic experiment is wonderfully rich in information content. But are there bits of the seismic waveform that perhaps we're not utilizing to the full extent? So let me give you the basic idea. And that is this, that it's very common practice in processing seismic reflection data to split the problem up into a problem of determining the model, which is sort of illustrated from Oz Ilmaz's book here on the left-hand side, an image of the seismic velocity model, and then to use that model to derive the seismic reflectivity image. And it's the image on the right that we would typically base our drilling decisions on, but we couldn't do without the image on the left. And for someone just starting out in geophysics, this is perhaps a little confusing because they're both representations in some sense of the Earth. The one on the left is color-coded in velocity, so reds are low velocities and blues and yellows, greens, and blues are higher velocities, and to some extent they show you a little bit about the geology, but it's the image on the right that really has the high-resolution, high-definition image of the structures. So the approach of waveform tomography that I'm going to be telling you about a little bit more now is first and foremost different from this common practice in that no distinction during the processing stage is made between the model. There's only one representation of the Earth. It's the model, it's the image, it's all in one. We're trying to use as much information as possible to contribute to the full spectrum of the result, the low wave numbers, the smooth part of the velocities, and the high resolution image. When I tell you a little bit more about how we do this, you'll immediately notice that there's a certain overlap in methodology, that it's very migration-like. But there is this significant change in philosophy. And to illustrate that, here's an image I'll be showing you again later in the talk. This is from our work at the EAGE workshop, BP Benchmark Velocity Modeling workshop in 2004. And the image is color-coded. In this case, it's blues are low velocities, and reds, in this case, in these regions here, represent salt bodies, high-velocity salt bodies. So the image is velocity-like in that it has information on the velocities and the actual quantitative values of velocities, but it's also got the high-resolution structural features embedded into it. The experiment here was deep water on the left-hand side, moving across to shallow water on the right-hand side. And you can see some of the layers and the sediments, subsea sediments, and so forth. So this image really has both parts of that of those goals present: low resolution velocity modeling, but quantitative, high resolution structural image. So with that sort of introduction to the basic idea, I'm going to give you this talk in 3 parts: long offset seismic data as an imaging opportunity. The industry is increasingly turning towards longer and longer offsets, longer distances between sources and receivers, and that gives us an opportunity to use parts of the waveform that we haven't really fully considered up until this time. So the way in which we're going to handle these new aspects of the data is this technique, which I call waveform tomography. So I'd like to tell you some of the theoretical aspects about it. It'll be a very visual demonstration, and then talk about the parts of the problem that I personally find the most satisfying is once you have this potentially very powerful mathematical technique, how do you engineer it to make it work in practice? And I'll finish up with a couple of additional examples, which I'll talk about when I get to them. So long offset seismic data. So let me introduce you to the 2004 BP velocity benchmark model. So BP built this model in a blind test in their lab to represent some of the challenges in imaging that they were facing. And the idea was that they would simulate seismic data from that model, distribute those seismic data to contractors, universities, other oil companies, and challenge people in a blind test to arrive at a workshop with their best possible image, using only the data without any knowledge of the model. So you can see the variety of different subsurface features that were included in that model. Very rugose top salt, a complex overhang on the salt body. Draw your attention to these low velocity anomalies over here, perhaps shallow sand channels that reduce the velocity and cause all sorts of imaging challenges. So, of course, they needed to shoot seismic data. And they shot the seismic data using a finite difference acoustic wave equation approach. And so they simulated a 15-kilometer streamer that was towed across the top of the model. Shots were fired every 50 meters. There were 1,350 shots altogether. The streamer length was 15 kilometers, and the peak frequency was about 27 hertz. So I'm going to illustrate some of those data to you now, but I'm going to show you those data in a little bit of an unusual format. They're going to look a little bit different from the shot gathers that you might be used to seeing. And the reason they're different is because we've low-pass filtered the data, brought out the low frequencies here, and we've applied a linear move-out that flattens the wide offset refracted arrivals. So out here, if you look on the bottom right, you can see the streamer location for this particular shot location. And you can see the refracted arrivals at the very far offset. So this is offset from 0 to 15 kilometers along the top, and data in reduced time from 0 to 8 seconds here. So we'll bring the streamer along. As you do, you'll see the waveform, of course, changing. Water depth will get shallower, so this water bottom reflection here will move up, and the refracted arrival will come in at earlier and earlier offsets. So we'll move the streamer along. There's another streamer position and another one further over. And I'm going to stop, sort of freeze the experiment right there, and have a little bit closer look at this particular shot gather. We're now in relatively shallow water, and our streamer is centered above those low-velocity channel features here. The refracted arrival gets there first when you're beyond 4 kilometers in offset. So these are all refracted arrivals here. And if you take a good look at the refracted arrivals, you'll see that the arrivals themselves are somewhat bright in some spots and dimmer in other spots. There is a sort of focusing and defocusing of the refractions as they pass through those low-velocity channel sands, which act as lenses. So the information about the channel sands is encoded into the seismic refracted wave field. It's almost like a problem in encryption. Here's the encrypted form of the model, and our job as processors and inverse theory scientists is to try to decrypt the model from that encrypted form. So waveform tomography is a method I'd like to highlight that's capable of decoding those refracted arrivals and eliminating the model. So first of all, for any inverse approach, the one thing that you need to begin with is an ability to model your data. So this is the modeling algorithm in action that we're using to simulate seismic data. This is at the core of the waveform tomography approach. It's, again, it's an acoustic finite difference approach. It's a fully two-way wave equation, so it's able to handle the situation that you're seeing unfold in front of you, in which the waves are entering the subsurface and they are turning back to the surface. So it properly handles the turning wave that is, of course, responsible for the refracted arrivals. Just to show you the model that lies underneath here, this is a sort of smooth version of that BP velocity model. The reds being high velocities, they cause, because of the increase in velocity with depth, they cause that turning effect. So that's how we simulate forward data. Now, there's another thing we'd like to do before we can turn to the inverse problem. And that is, we'd like to answer the question that all people who look at seismic models eventually ask, which is, what if I change the model? What if I move the velocities around? If I change the velocities at a certain point in the subsurface? What are the new data going to look like? How does that translate into a change in data? So it's a perturbation question we're asking here, and the equation you see at the top is the Born approximation to the answer to that equation expressed in integral form. But don't worry about that equation. I'd like to show you this visually. So let's go in and perturb the model. So we're putting in a box-shaped perturbation at this point in the model, and that's going to be our change in slowness parameter here. That change in slowness parameter interacts with the incoming wave to create a virtual source of scattered energy. So this virtual source is sort of radiating energy as time evolves. So let's see what happens to that radiated energy. So now we're looking at all three terms in the equation here, the perturbation, the incoming wave, and the wave that is radiated out from that perturbation. You can see that wave radiating forward, in this case, towards and upwards towards the receiver streamer. Now some of that energy gets backscattered and contributes to the reflection waveform. But most of it, the largest portion of it, gets forward scattered. So the forward scattered energy here is moving up towards the receiver line. Okay, so let's now turn this around and say, okay, suppose I did this experiment. I had some idea of the starting model and I did the experiment. I discovered there were waveform differences. What should I do with those waveform differences? How could I use those waveform differences to discover where this anomaly is? So the simple intuitive thing that many, many people have done, and it lies at the heart of many migration algorithms, is to do the following. Take those data differences and insert them into the same modeling algorithm, but allow time to run backwards. So we're now running the same equation backwards in time, and these waves are propagating back into the model. Now notice they're coming into focus. We've got an array here. The streamer itself acts like an array, and they're coming into focus in the area in which the model has been perturbed. So we're learning something by doing this. You know, we see things coming into focus in the right sort of places. It's an intuitive thing to do, and it works. But it's not yet an image. So how could we turn this idea into an image? And the answer, for those of you who are at all familiar with migration theory, is to apply an imaging condition, which is to take that back-propagated wave field in the central panel and to take that back-propagated wave field and multiply it by the forward-propagated wave field that we started out with at the top. If you do that multiplication, you get this curious-looking banana-shaped anomaly. Now that is a fully implemented image of the anomaly using only one source and one frequency. You can see it is coming into focus in the right location, just about here, but this banana shape that's sort of popping out at you is not really an ideal image of a box. Well, it's not an ideal image because we've only used one source. So let's go ahead and do the same thing with all the source positions and superimpose all of those images together. Now, when we do that, we start to see something. Now we're looking at a fairly reasonable image of the perturbation at the right place. It's not the greatest of images. It suffers from these artifacts, these butterfly wings that you can see jumping out at you. But again, we've only used one frequency here, and we haven't yet done any iteration. And it's quite possible to iterate this method. Our wave equation modeling method here is able to handle all sorts of velocity distributions, so we can go in and change the velocity distribution, update the velocity distribution to take into account of this image that you see, and do the whole thing again. So if we iterate, we can come up with a final image, many sources, many frequencies, many iterations, and apart from some side lobe energy here, you can see a fairly good image of the actual perturbation. So what I've done here is I've taken you through the whole procedure. By the way, the equation at the top here looks a little bit like the equation we started out with, but it's not. You see the term over here, the slowness perturbation has moved over to the right, and the data perturbation has moved inside the equation. This is an exact equation for the gradient, so-called gradient of the misfit function. So this equation here really lies behind the algorithm, except we apply it iteratively. Now, what you'll notice is that we've been able to reconstruct the smooth part of the velocity anomaly. We've actually been able to reconstruct, there's no color bar here, but we could have put one on. We've been able to reconstruct the velocities quantitatively. And that's partly because we've been using wide-angle information, wide-angle refracted information, which is very sensitive to the velocities. All right, so I've more or less taken you through the theoretical aspects of the method. What I'd like to do now is take you back to that BP data set and show you how we make it work in practice. So again, it's not a great slide from where you're sitting, I'm sure. We'll improve it in a moment. But shot gathers. we received a whole load of shot gathers via BP's FTP server, and that was all the information we had, apart from some details about the geometry. This was all the information we received. Now, that shot gather shows a very clear water bottom reflection here, a refracted portion of the wave field here, a fairly significant multiple sequence. Let me move on to the next one. You can see it a little bit better. So one of the first things we did was to flatten the refractions, apply a linear move out so we could see them better, and to pick all of those data, to pick the first arrivals, so that we would then have the opportunity of coming up with a model that fit those arrival times. So let me show you that. First of all, we're going to develop a model that fits those picked arrival times using standard ray trace approach for travel time tomography, using those diving waves. And after a few iterations, you come up with a model. This is a few nonlinear iterations. You come up with a model that shows some of those velocity distributions. It's not a very well-focused image, and that's perfectly expected. You're simply fitting times. You're not fitting waveforms. There's only a limited amount of information in those times. To show you some of the ray paths for that image, this is really giving you the message here that using those diving waves, we're really only going to be able to see down to 5 or 6 kilometers maximum. So you really should take a large grain of salt with the bottom part of the image here. This is all extrapolation and not at all representative of what the velocities down here look like, because those arrivals are not sensitive to that portion of the model. But above 6 kilometers, in that sort of critical near-surface velocity problem, we've done a pretty good job of covering the model with rays. So let's go back to the waveform data, some low-pass filtering, some time windowing, and we're now going to try to come up with a model that doesn't just fit those times, but it fits all of the waveform information. These complicated waveforms that you see here that are coded versions of the model, we want to predict them. We want to come up with a model that predicts them adequately. So we'll start introducing data, waveform data, into this model here. From where we start from here, from the travel time model. We've got some information on the bathymetry as well, and we'll start iterating. So at this stage, we've introduced some very low frequencies into the data, into the modeling aspect here. We're only moving up to 3.5 hertz, but even at those very low frequencies, because we're properly accounting for waveform effects, we're able to see some of the structures almost immediately. So we'll continue introducing more data and going up eventually to 7.5 hertz. And at this stage, no higher. This was the final result here that we obtained after iterating through all those frequencies. So we're up at 7.5 hertz. Very low frequencies, but we're able to see quite a lot of structure in the model. Now you have to perhaps put yourselves in our position at the stage we saw an image like this. We didn't know anything about the subsurface model, except that maybe BP might be interested in salt structures, and so seeing velocities 4 to 4.5 thousand meters per second wasn't perhaps that unexpected. But were these structures over here on the left-hand side at all realistic? We knew that we shouldn't trust the image below 6 kilometers, but we didn't know, right? We had to simply show up at the workshop and put our results on the table and leave ourselves open to the possibility that we'd got it all wrong. Well, we didn't. There's the comparison with the true model. This is BP's color scale, and they've correctly sort of grayed out the bottom part of the model here to illustrate that that's the part where there's no refracted energy penetration. So down here, we're not trusting the model very well. But the portion of the model that we did claim to resolve, we did a fairly good job. And the structures here were very clearly related to the structures that were actually present. And you notice how successfully we've found those low velocity channels in this region here. So this was reasonably successful. And I'll point out again, we were the only group that used the refracted energy. We focused entirely on the refracted energy in this reconstruction. So it sort of illustrates the principle here that you can use those refracted arrivals in some very sophisticated ways to get a very good resolution image. Although normally we associated refraction methods with low resolution, you can actually get some very high resolution images. And remember, we've only done this up to 7.5 hertz. Well, this slide is intended to sort of segue into the next portion of the talk, in which I claim that we can use this approach or to use this experiment, in fact, to predict what might happen at some very, very different scales. So the scale modeling that was done by BP, of course, simulated at 10 hertz wavelengths of the order of 200 meters, and that arrow that you see in the middle here is the number is a 100 wavelength bar at that 10 hertz frequency, just to give you an idea of scale here. A 100 wavelength bar would also fit if we had divided the frequencies by 10 and multiplied the distances by 10. So let's just say, for example, and I'm sure most of you, being industry people, would not be that interested in looking at the deep crust in the upper mantle, but if you were an academic who was interested in doing that, and you had a very low frequency source and some low frequency receivers, you could look down at the base of the crust in the upper mantle using distances of the order of 200 kilometers instead of 20 kilometers. Same scale modeling principles apply. This predicts what you would be able to do at those scales. So we've gone and done that, and I'm not going to have time to take you through those results today. And the other thing that we've done is we've done something quite radical. We said, well, what if you multiplied the frequencies by a factor of 1,000,000? And then you'd have to divide the distances by a factor of 1,000,000. Well, then you'd be at the ultrasound scale. Megahertz frequency, 10 megahertz frequency, 20 millimeters by 50 millimeters. Samples that you could hold in your hand, put in the lab, and so forth. All the modeling that you've seen so far in this talk is applicable to that scale as well. So further examples on the talk, I would talk a little bit more about deep crustal imaging and then medical imaging applications. Just to explain to you, that deep crustal example was another workshop example, another blind test. Same procedure we followed there. This has been written up and published, and there's a reference for you if you'd like to look that up. I do want to show one slide from that study, though, and that is to illustrate a comparison between the quote-unquote real data from that benchmark study over here on the left and the synthetic data predicted, first of all, in the starting model. Now, if you look at the data in the starting model, the arrival times at that green arrow there is pretty close to the arrival time of the data. So our starting model predicts the arrivals. But obviously, if you look at those data, they're far more complex for the real data than they are in the starting model over here. After we go through the whole iterative procedure, we come up with a very complicated waveform that matches the original waveform in quite some detail. And that's the objective here, and that's the way in which we can judge the success or otherwise of our methods without actually knowing the ground truth. At least we've come up with a model that simulates some of these very subtle features, a shadow zone here, a step back to later arrivals, a reflection down here. So there are some very complicated features here that we've been able to predict. Okay, I did want to indulge myself a little bit and show you some of our results with medical imaging, and that's what will conclude this talk here. I've been fortunate to link up with the Karmanos Cancer Research Institute in Detroit, and specifically Neb Durek, who's provided me with these images of their imaging tank and ring array. Now, this is not simply an experiment for fun. This is a cancer research clinic, and they are undergoing clinical trials with patients now. But here's their transducer system. There are 256 elements in that transducer system, in that ring. And each one of them can be fired independently, and the other 255 can be used as receivers. So they're pinged in turn all the way around the ring. We get 256 shot gathers, as it were. The typical way of testing imaging capabilities in the medical industry is to build what's known as a phantom. So this is the University of Wisconsin gel breast phantom intended to simulate cancerous breast tissue. So this is actually an X-ray that you're looking at here, and the only thing I'm using this for at this stage is just to point out to you that there is about 100 wavelengths at ultrasound frequencies from one side to the other. So this is a scale model of the expiration scale refraction experiment. Perhaps I should point out some of the features on that phantom. There is a quarter millimeter skin layer around the phantom. There's a subcutaneous fat layer and a glandular tissue in the center here that is disturbed by 4 simulated masses, 2 of which are simulating high-density, high-velocity tumors, and 2 of which are simulating low-velocity, low-density cysts, fluid-filled, non-cancerous cysts. Well, let's have a look at some data. So those of you looking at this display, many of you looking at this display will recognize that I'm using Promax to display the data from the breast phantom. This is a shot gather. Receivers all the way around the ring. As you go around the ring, as you get to 180 degrees, the times get longer and longer and longer, the arrival times here. And then as you continue going around the ring, they get shorter. Well, the first thing that we did when we got these data was to apply a flattening transformation on the first arrival. So there's the same data flattened to highlight the first arrivals. We can then zoom in on the first arrivals. So we're now zooming the time scale here and having a really close look at those first arrivals. And they look, to me, a lot like seismic data, and I'm sure they do to you as well. You can see some of the features I pointed out at the very beginning of the talk for long offset seismic data in terms of brighter and dimmer spots here. These are encoding the presence of those anomalous masses within the phantom. There are clear reflections from the skin layer of the phantom on the edges over here. So the structure of that phantom is coded up into these arrivals. Well, we did the whole procedure. We picked arrival times. We did travel time tomography in the result. And we did waveform tomography in the result. And you can see the resulting differences here. On the left-hand side, travel time tomography, fairly low resolution image of the phantom. That's the phantom here. Everything outside the phantom is water. It's supposed to be 15, 20 meters per second. There are some artifacts in the image here due to the transducer, some issues with the transducers. You can see the subcutaneous fat, the high velocity and low velocity anomalies within the phantom itself. On the right is the waveform tomography reconstruction. So this model here fits the waveforms, not just the travel times. First thing that pops out at you is a white circular layer. That's the skin, the simulated skin of the phantom. Very, very reflective skin layer. Subcutaneous fat, high velocity anomalies here, low velocity anomalies. I'd like to zoom in on that image now. So we're zooming in on those two images, on the left travel time and on the right waveform tomography. Notice that you can now see very clearly the location of the low velocity, small size, low velocity simulated cyst here. What we'll do now is we'll take the X-ray and gradually merge it to the waveform tomography result a couple of times so you can perhaps convince yourself that this ultrasound result is doing a fairly good job of reconstructing the actual geometry of the phantom. Now, we've also gone on and applied this imaging methodology to some clinical data from patients who are indeed suffering from breast cancer. Those results are written up in the SPIE, and they can be accessed. So I won't have time to show those results today. So I'm going to finish up now. Just to recap, I began by talking about long offset seismic data and refractions and what refractions can potentially do for you. I showed you how we can use those refractions to generate models using waveform tomography, and I've extended those to a couple of other examples outside the sort of exploration scales. So where are we going with this? Well, there's a lot of different applications that you can dream up that would be suitable for this approach, and some of them we're working on. And specifically, I'd like to finally draw your attention to the exploration seismic data scale of things. So we've been very fortunate that Talisman Energy and Sylvester Charles of Talisman Energy have entered into a research agreement with us, and this is a velocity model that's been sort of jointly agreed on with Talisman to simulate some of the foothills imaging problems, a little bit closer to home for most of you, I guess. The sharp topographic relief, high velocity layers outcropping in places here, the overthrust geometry of the geology, and so forth. Now, all I'm going to be able to show you today is a sort of preview of results that we're hoping to present at the convention in a few weeks. But on the right are model data predicted in the model I've just shown you, whereas on the left are some field data that Talisman have donated to the project. And if you look at these two, obviously they're not the same. We're not doing any waveform fitting yet, but we're capturing a lot of the effects of the topography, the sort of diffraction effects of the topography shown here, matching up with some of the diffraction effects that you can see in the real data. We haven't simulated in the synthetics, we haven't simulated the ground roll. This is an acoustic modeling procedure that wouldn't do that. We wouldn't expect to see it. But the wide-angle reflections and then generating wide-angle refractions are captured pretty nicely here. So we're pretty excited by the prospect that we might be able to apply this to problems in the Alberta foothills. Well, if this has sparked your interest, Rob mentioned at the beginning that we're running a school at Queen's, and there's some details of it. If you simply Google Waveform Tomography 2008, I'm pretty sure that'll come up first, and you can find out more about that. We do still have space on that course if you're interested. And I'll finish here with my acknowledgements, specifically Drew Brenders at Queen's, my lead PhD student at the moment, and Sylvester Charles of Talisman Energy for getting involved in this, and Neb Durek of the Karmanos Cancer Research Institute, as well as the other graduate students that have contributed over the years to these approaches and other collaborators. So thank you very much for listening.